To all my fellow struggling electrical engineering students, today in Struggles with Electrical Engineers, we're going to Semiconductor 101 Part 2. I discussed diodes and Zener yesterday, the PN junction, depletion region, and barrier potential. All these concepts are fundamental to understanding transistors because transistors are a semiconductor device just like diodes, and in fact, one of the simplest ways we can model transistors is using the two-diode analogy. This is taken straight from Caltech and almost every other textbook on Earth. It's not a perfect model, but it'll give you an idea. You can kind of think of an NPN transistor, an NPN BJT transistor, as a sandwich of two diodes right here. So you see this diode going towards the collector, this diode going towards the emitter, and I've kind of labeled the N and P region. So this is the P region, this is the N region. So BJTs are a sandwich, sort of like BLTs, but don't eat them, as one of our profs did mention. Alright, so the BJT has two functions. The first and primary function of a BJT is switching, because there are far superior transistors for amplification. That does not mean, though, that a BJT should not be used for amplification. Alright, there are three regions of operation for a BJT. There's the active region, there's the cutoff region, and there's the saturation region. Now, the active region is where it performs normally. The cutoff region is essentially where there is such low current to the base that you receive nothing out, and saturation is when it is maximum cranked. So I just mentioned current to the base. I got a little bit ahead of myself, but BJTs are a current controlled device, and I'll explain in a second. So this is an NPN transistor. The reason we know it's an NPN is because this diode symbol is pointing to the emitter. Now, in a PNP, this would be facing the base. A simple way to remember it is the diode always points towards a positive, a P layer of the semiconductor. So in this case, with it being NPN, the base is N, C is P, and E is P. It always does go along the emitter, so if it's NPN as such, it will be going down to the emitter. If it's PNP, it will be going from the emitter to the base. So these three regions, collector, base, and emitter. The really cool thing about BJTs is that they're current controlled devices, and what that means is a small current at the base causes a large current to flow from the collector to the emitter. Next, we haven't really explored BJTs too far in our lectures, and therefore I won't go further than the professors, just so that in case they teach it in a different way, I don't want to confuse you, but I will take you through the basics. In terms of amplification and a lot of other things in general, all transistors have an alpha and a beta ratio. And the alpha is the ratio between the collector current and the emitter current. So this would be the current flowing into the collector as such and out of the emitter. Now I'm talking about specifically NPNs because that's mostly what we use. The beta of a transistor is the relationship between the current flowing into the collector and the current flowing into the base. So as we know, there's a direct correlation between the amount of current we push through the base and what comes out of the emitter from the collector to the emitter and out. Essentially, these are just simple ways to remember Kirchhoff's law. That's all it is. It's simple Kirchhoff's law, as we've done with simple circuits before semiconductor devices. We can calculate IE from IC plus IB, or from their alpha and beta as well. And these are other relationships as well that have not been taught in class, but it would be good to know them. Now, one of the important things you guys will need to learn how to do is to test a transistor. Alright, when you're testing an NPN, remember this, you always want to place your main test lead on the base. So in case of NPN, because the base is positive, you want to put the red lead on the base. Once you put the red lead on the base and measure in diode checking mode, the other two junctions, or the other two wires or legs, you should get about 0.7. Again, as I explained yesterday, 0.7 always for silicon on both ends. Now, if you're dealing with a PNP, which is rare, but it might come up on a test, you want to put the black lead on the base, on the end, and the red lead on the emitter and the collector, and you'll get 0.7 and 0.7. So just remember that. If you're putting your red lead on the base and you're not getting 0.7 on the emitter and collector, that means you have a PNP, which will be rare for us, I promise. Now, after this 2-diode model, sandwich model, this is the true circuit symbol. This is sort of how they work. And this is a very physics-heavy example of how they work. All you really need to know is current flows up, and by current, we're talking about holes, depletion regions, and barrier potential, as I discussed yesterday, are in 2 locations on a transistor instead of just 1 on a diode. Diodes have 1 junction, transistors have 2. Actually, there are transistors that have more than 2 junctions, but we're not getting into that till next year. Essentially, this is what happens. So, as we apply current to the base, holes flow towards the emitter as electrons flow to the collector. Alright, that sounds complicated, right? But here's the best part. You really don't need to be able to regurgitate that. What you need to be able to say is, I apply current to the base, and the current from the collector to the emitter increases. So, just remember this. Current is always flowing into the base, it's flowing into the collector, and it is flowing out of the emitter. And that is where we get our usable amplified current. I know this was pretty basic, but these are the fundamentals, and I really would not want to deviate from the way the professors are teaching the course, just in case they do it some different way. I'm always here for help. Ask me any questions you need to once we have our next round of lectures, but I do believe this is pretty much all that we've covered. Anyways, thanks a lot.